let's say that I have a huge, maybe frozen over lake, or maybe it's a big pond. So I have a huge surface of ice over here. My best attempt to draw a flat surface of ice. And I'm going to put 2 blocks of ice here. So I'm going to put 1 block of ice just like this, 1 block of ice right over here, and then I'm going to put another block of ice right over here, and then another block of ice right over here. And these blocks of ice are identical. They're both 5 kilograms. They are both 5 kilograms. Let me write this down. So they are both 5 kilograms, or both of their masses, I should say, are 5 kilograms. And the only difference between the two is that relative to the pond, this one is stationary. This one is stationary. And this one is moving with a constant velocity. Constant velocity in the rightwards direction. And let's say that its constant velocity is at 5 meters per second. 5 meters per second. And the whole reason why I made blocks of ice on top of ice is we're going to assume, at least for the sake of this video, that friction is negligible. Now, what does Newton's first law of motion tell us about something that is either not in motion, or you could view this as a constant velocity of 0, or something that has a constant velocity? Well, Newton's first law says, well, look, they're either going to keep their constant velocity or stay stationary, which is a constant velocity of 0, unless there is some unbalance, unless there is some net force acting on an object. So let's just think about it here. In either of these situations, there must not be any unbalanced force acting on them, or there must not be any net force. But if you think about it, if we're assuming that these things are on Earth, there is a net force acting on both of them. Both of them are at the surface of the Earth, and they both have mass. So there will be the force of gravity acting downwards on both of them. There is going to be the downward force of gravity on both of these blocks of ice. And that downward force of gravity, the force of gravity, is going to be equal to the gravitational field of near the surface of the Earth times, which is a vector, times the mass of the object. So times 5 kilograms. 5 kilograms. This right over here is 9.8 meters per second squared. So you multiply that times 5, you get 49 kilogram meter per second squared, which is the same thing as 49 newtons. So this is a little bit of a conundrum here. Newton's first law says an object at rest will stay at rest, or an object at motion will stay in motion, unless there is some unbalanced, or unless there's some net force. But based on what we've drawn right here, it looks like there's some type of a net force. It looks like I have 49 newtons of force pulling this thing downwards. But you say, no, Sal. Obviously this thing won't start accelerating downwards because there's ice here. It's resting on a big pool of frozen water. And so my answer to you is, well, if that's your answer, then what is the resulting force that cancels out with gravity to keep these blocks of ice, either one of them, from plummeting down to the core of the Earth, from essentially going into free fall or accelerating towards the center of the Earth? And you say, well, I guess if these things would be falling, if not for the ice must be providing the counteracting force. And you are absolutely correct. The ice is providing the counteracting force in the opposite direction. So the exact magnitude of force, and it is in the opposite direction. And so if the force of gravity on each of these blocks of ice are 49 newtons downward, it is completely netted off by the force of the ice on the block upwards. And that will be a force of 49 newtons upwards in either case. And now, hopefully, it makes sense that Newton's first law still holds. we have no net force on this in the vertical direction. Actually, no net force on this in either direction. That's why they have a constant velocity. This guy has a 0 velocity in the horizontal direction. This guy has a constant velocity in the horizontal direction. And neither of them are accelerating in the vertical direction. Because you have the force of the ice on the block, the ice supporting the block, that's completely counteracting gravity. And this force in this example is called the normal force. This is the normal force. It's 49 newtons upwards. This right here is the normal force. And we'll talk more about the normal force in future videos. The normal force is the force when anything is resting on any surface that's perpendicular to that surface. And it's going to start to matter a lot when we start thinking about friction and all the rest. So what we'll see in future videos, when you have something on an incline, and let's say I have a block on an incline like this, the normal force from the, I guess you could say, this wedge on the block is going to be perpendicular to the surface. And if you really think about what's happening here, it's fundamentally an electromagnetic force. Because if you really zoomed in on the molecules of the ice, right over here, or even better, the atoms of the ice here, and you really zoomed in on the atoms or the molecules of the ice up here, what's keeping this top block of ice from falling down is that in order for it to go through, its molecules would have to kind of compress against, or I guess it would have to get closer to the water molecules or the individual atoms in this ice down here. And the atoms, let me draw it on an atomic level right over here. So maybe let me draw one of this guy's molecules. So you have an oxygen with 2 hydrogens. And it forms this big lattice structure, and we can talk about more of that in the chemistry playlist. And let's talk about this ice is one of these molecules. So maybe it's down, maybe it looks something like this, and it has its 2 hydrogens. And so what's keeping these guys from getting compressed, what's keeping this block of ice from going down further, is the repulsion between the electrons in this molecule and the electrons in that molecule. So on a macro level, we view this as kind of a contact force. But on a microscopic level, on an atomic level, it's really just electromagnetic repulsion at work.